the next couple of lectures we will discuss quantification. Predicate logic has two types of quantification: universal quantification and existential quantification. In this and the next lecture we will focus on quantification of unary predicates. In later lectures we will also consider quantification of predicates of higher arity. Consider the statement, for all natural numbers x, it holds that 4x is less or equal 5x. Although this statement is based on a unary predicate, by saying that the unary predicate should hold for all natural numbers, we're actually turning it into a proposition. The thing is that we can evaluate this statement without committing to a particular value for x. If 4x is less or equal 5x holds for all natural numbers x, then we say that the statement is true. Whereas if 4x is less or equal 5x evaluates to false for some natural number, then we say that the proposition is false. We will introduce into our logic a universal quantifier, which is denoted by an upside down A. It is applied to two predicates, separated by a colon and enclosed in square brackets. The predicate before the colon restricts the domain of quantification, whereas the predicate after the colon is the actual predicate that is being quantified. Let us now introduce universal quantification more generally and discuss its interpretation. We introduce for every variable x a symbol that is written as an upside down A with x as a subscript. These symbols are called universal quantifiers, and we use them to express universal quantifications as follows. Let P and Q be predicates that may or may not refer to some variable x. For clarity of presentation, we add the x between parentheses. This has no formal status, but serves to remind you that the x could occur in the specification of the predicates. Then we express the predicate for all x satisfying P also Q holds with an application of the universal quantifier associated with x to the predicates P and Q. The predicate P, which intuitively specifies the domain of the quantification, appears before the colon. The predicate Q, which is thought to be quantified, appears after the colon. Formulas that have a universal quantifier as main symbol, as you see here, are generally called universal quantifications. Let's return to our example. For all natural numbers x, it holds that 4x is less or equal 5x. We shall try to give you some further intuition for the interpretation of universal quantification by extending the analogy introduced before, in which predicates are considered as little programs for devices producing truth values as output. According to the analogy, a unary predicate, such as 4x is less or equal 5x, may be thought of as a program for a device that produces a 1 on its output port if the predicate 4x is less or equal 5x evaluates to true for the natural number x we put on its input port, and to 0 otherwise. Now imagine that we attach the input port of this device to a so-called generator, which is thought to exhaustively generate all natural numbers, one by one. And imagine that we attach the output port of the device to a so-called universal verifier, which monitors the output port of the device. The idea is that this universal verifier produces a 1 when the evaluation of the predicate 4x is less or equal 5x yields 1 for every generated natural number, and a 0 if at some point it turns out that 4x is less or equal 5x evaluates to false on some natural number. The result is a device that does no longer have an input port. It is thought to evaluate the predicate 4x is less or equal 5x for all natural numbers x, as you see here. The device should produce a 1 on its output port if all of these evaluations result in true, and a 0 otherwise. And since the predicate 4x is less or equal 5x evaluates to true for all natural numbers x, this device produces a 1. Now we should issue a warning. Although I believe that the analogy gives you a good operational intuition for universal quantification, it is also a dangerous analogy. Clearly, it is not a realistic scenario to generate all natural numbers x one by one and successively evaluate the predicate 4x is less or equal 5x. Since there are infinitely many natural numbers to generate, this process will not be completed in a finite amount of time. From a logical perspective, however, the evaluation of the universal quantification is instantaneous. So to appreciate the analogy, you should completely ignore the timing aspect. The analogy serves to give you an intuition for the truth value assigned to the universal quantification, but should not be considered as a feasible recipe to actually find that truth value. Let's now consider the example of universal quantification again, but slightly change the predicate involved. We replace the less or equal predicate by the less than predicate. Then, running the device again, when the generator generates the natural number 0 for x, the predicate 4x is less than 5x evaluates to false. For all the other natural numbers x, the predicate 4x is less than 5x evaluates to true, but that is no longer important for the evaluation of the universal quantification. For all natural numbers x, it holds that 4x is less than 5x. By the mere fact that there is some natural number x for which 4x is not less than 5x, this universal quantification evaluates to false. The device produces a 0. Next, consider the statement, there exists a natural number x such that 4x is less than 5x. This statement is again based on a unary predicate, 4x is less than 5x, but by preceding it with the phrase, there exists a natural number x, we are actually expressing that we do not intend to evaluate this unary predicate for some particular value of x, but rather we wish to know whether there exists some natural number x such that the unary predicate evaluates to true. If such a natural number x exists, then we assign the truth value true to this statement. If there does not exist such a natural number x, then we assign the truth value false to this statement. And thereby, the statement is a proposition. We can assign a truth value to this statement without committing to a particular value for x. We introduce existential quantification into our logic by means of existential quantifiers. These are represented by mirrored e's in our notation. Existential quantifiers are applied to two predicates, separated by a colon and enclosed in square brackets. The predicate before the colon restricts the domain of quantification, whereas the predicate after the colon is the predicate that is actually quantified. Let's now introduce existential quantification more generally into our logic and also discuss its interpretation. For every variable x, we introduce a new symbol that is written as a mirrored e with x as a subscript. These new symbols are called existential quantifiers, and we use them to express existential quantifications as follows. Let p and q be predicates that may or may not refer to some variable x. Again, for clarity of presentation, we add the x between parentheses. Then we express the predicate there exists x satisfying p that also satisfies q with an application of the existential quantifier associated with x to the predicates p and q. The predicate p, which intuitively specifies the domain of the quantification, appears before the colon. The predicate q, which is thought to be quantified, appears after the colon. Formulas that have an existential quantifier as main symbol, as you see here, are generally called existential quantifications. Let's consider the interpretation of our example. There exists a natural number x such that 4x is less than 5x. We again attach the input port of the device corresponding to the predicate 4x less than 5x to a generator, which is thought to exhaustively generate all natural numbers. And then we attach the output port of the device to a so-called existential verifier. It is similar to a universal verifier in the sense that it monitors the output port of the device, but it is different in the sense that it produces a 1 if the generator at some point generates an x for which 4x is less than 5x, and a 0 if the generator never produces such an x. So, the resulting device can be thought to evaluate the predicate 4x less than 5x for all natural numbers x and produce a 1 on its output port if at least one of these evaluations results in true. It produces a 0 otherwise. Although 4x less than 5x evaluates to false if x is equal to 0, there are other natural numbers x for which 4x less than 5x does evaluate to true. So the device associated with there exists a natural number x such that 4x is less than 5x produces a 1. Let's consider one more example with existential quantification. We replace the less than predicate by the greater than predicate. Then, running the device again, since for every natural number x, the predicate 4x greater than 5x evaluates to false, the existential verifier will never see a 1. Therefore, the device thus associated to there exists a natural number x for which 4x is greater than 5x will produce a 0. We have introduced two new constructions in our logical language: universal quantification and existential quantification, and we have explained their meaning. The notion of quantification that we have introduced uses a predicate to restrict the domain of quantification. In the next lecture, we shall study the domain of quantification more closely.